Okay, so I will I will give a presentation about some recent results about change point asymptotics in a multivariate situation for covariance matrices. If you have high-dimensional time series, I will first give a brief introduction to the problem and discuss also some examples. Discuss at least two types of models which are very commonly used in applications in many areas. And where the results apply. Then I will present the change point test, first for a single Q-sum statistic and then also for a multivariate version. Discuss the theory and discuss a little bit, perhaps some simulation example in case that there is enough time. So the results are mainly based here on this first paper, which is under revision, and the other two papers here, which already appeared, are, in a certain sense, the backbone, which is, however, also extended, and there are further papers. If you have, for example, there are two projects from PhD students. I will not discuss the details of their specific problems, so vector models and K-sample setting. So I will discuss this case here, which is the change in the covariance matrix. And the idea is to have multivariate versions of the statistics. You will see it in a second. So we all know that high-dimensional covariance matrices play an important role in many areas. In metrics, spatially distributed sensors are a big topic, production engineering, quality control, biotechnology, statistical genetics. Everywhere we have large data sets, many variables, and also in some cases a lot, so big number of observations, but sometimes the dimension is even larger than the sample size. And here are perhaps some very first motivating examples. Suppose you want to detect a change in a covariance matrix or part of it. Then you can extract subsets, for example, by simply looking into the object by forming bilinear forms, A prime sigma B, where the vectors are 0 or 1, and the L0 norm is bounded. For example, if you want to make some kind of screening, you have some candidate variables, for example, genes in a statistical genetics application, and they are up to the index nu star. And you want to compare with the rest of the genome, so these are kind of noise variables. Then you can define your vectors, your weighting vectors in this way. You take here an average of the candidate genes, for example, and the other entries are of this type so that they are summable. And this, of course, quite naturally leads to the case that if we look into a covariance matrix by bilinear form, then we also want to study, for example, some kinds of contrasts. So this means we would need also a multivariate version. Here's one data set which I perhaps discuss a little bit. Here are spatial distributed sensors measuring climate in the United States. There are 440 sensors, so climate monitoring stations. And so, for example, if you take ozone measurements, then it is known that ozone is generated locally by photochemical process, but there's also some kind of local transport simply because of wind. So an appropriate model which has been used for such data for the mean-corrected ozone measurements is a Warmer model, where you can model that the correlations also are induced by this kind of local transport with respect to different time lags. If you have such spatially distributed sensors, suppose we have D observed variables distributed over R regions, for example, states. This can be represented by classification easily. This means we have a partitioning of the index sets of the variables. If you know the memberships, then we can very easily define an orthogonal system of weighting vectors. The inner products are simply the region-wise averages, have a very nice interpretation, but usually you do not know the memberships. One way to estimate them is to estimate sparse eigenvectors from a learning sample. Then the idea is, of course, that the measurements from one region are correlated, but the regions are uncorrelated. So we want to estimate some sparse eigenvectors, and then you look at the support of the eigenvectors, and this gives you the kind of segmentation of your variables of your sensors. The inner products are then, again, have a nice interpretation. They are kind of weighted cluster averages. So the basic idea is to look at projections. We have a projection statistic W prime Y for weighting vectors W. And a crucial assumption for part of the theory is that the L1 norm is bounded uniformly in the sample size. But if you do statistics and look at standardized statistics, then it is sufficient if they are L2 bounded uniformly in the sample size. Two projections have a covariance given by our bilinear form. This means we are also analyzing naturally, correlation structures, covariances between projections. If we want to base our analysis on this type of statistics, so the bilinear form where we plug in the sample covariance matrix. And the class of models where this works, where the assumptions are satisfied under quite weak regularity conditions, are stable Warmer processes of this form. Yes, I think I do not have to explain the model in detail. Where the noise, multivariate noise here, the innovations are allowed to be colored approximately. And the weighting matrices, of the Warmer model, these have to satisfy a weak decay condition. And here some constants arise, which for the technical construction, which need to satisfy a weak summability condition in order to get the results. And another model which is quite popular in high-dimensional statistics is the spike covariance model. Yes, here we assume that the covariance matrix is given by this in this form. Yes, so we have here the eigenvalues, the leading eigenvalues are lambda j plus sigma squared. So they are spiked, therefore the name. And the rest of the spectrum is flat, given by sigma squared. This has been studied a lot. We all know the famous result from Johnstone and Liu, for example, that PCA in general is then not consistent if the dimension is proportional to the sample size. This has been studied in greater detail, and the idea came to use sparse PCA in order to get consistent estimates, and then you have to make assumptions on your eigenvectors usually. The results have been refined during the course of time. The most recent results, for example, they consider assumptions, sparseness assumptions on the row support of the metrics of the eigenvectors. For example, here in this work, so we need sparseness of the row support. And there's also a more recent result, which also does asymptotic theory in the sense of CLTs, in case that it allows for diverging eigenvalues. And Lajos also has a quite new result in this direction, looking at theory for an eigenvalue. So the change point model I want to study is that we have two sets of coefficients. These are the coefficients for a linear time series model, or the moving average representation of the Warmer model, and satisfying the required decay assumptions. And we look at the covariance matrices under these two sets of coefficients, and we assume that for these two sets of coefficients they are different. So we're going to detect the change from one covariance structure to another one, and we pick weighting vectors such that the difference in the bilinear forms is not zero. And for consistency, we shall assume that the infimum over the delta n is positive, respectively, that it converges to some value delta, which is positive in absolute value. The change point is denoted by tau, and so we assume that up to tau, we are given a time series model of these set of coefficients b before change, and then after the change point, the coefficients are given by the array c. And so in terms of testing problem, we are interested in testing whether tau is equal to n. This means we have no change point within our sample, and the alternative is that we have a change point in the sample where the covariance matrices change. The change point procedure is based on the partial sums of the outer products y and I prime of our high-dimensional time series. Here I assume throughout that the expectation of the time series is 0, yes, because we are interested in second-order analysis. But it can be shown that in case that it is not, we can center the time series in a kind of pre-step as usual. And still most of the results go through. And then we form our bilinear forms with our weighting vectors v and w. So these are the u and k. The d and k are the centered versions of these bilinear forms. And then we look at the Q-sum statistic. This is the usual Q-sum statistic where we center at the sample average, the u and k's, and this can be also written in this form. And for candidate point k, then we compute this and look for the k where this is maximum. Okay, so and if you look at the expectation of these guys which are used to form the Q-sum statistic, you get these simple formulas. And we see that depend, of course, on delta n, which is nice, the difference in the bilinear forms. And here first, if this is positive, for example, then this is first an increasing function until tau, and then it decreases. So this gives also a way to estimate the change point. If we want to test, then we reject the null hypothesis in favor of the presence of a change. Yes, if this Q-sum statistic seeks critical value, and here we standardize by some estimate of the right asymptotic variance of these u and k variables. And here we can use in this situation, because it turns out this can be approximated by Brownian bridges, supremum over Brownian bridge process, that we can use the Kolmogorov distribution. The estimator I will discuss later.
The dimension is fixed, right?
The dimension is not fixed. The dimension can depend on n and tend to infinity. And actually it turns out that these results hold true without a constraint on dimension over sample size. So it's not required that they're proportional to sample size. They can grow at any rate, actually, which was a bit surprising. So there are not so many results in this direction. So one can also look at the weighted Q-sum statistic. So we do introduce a weighting function g depending on the k over n. And yes, this compensates for the fact that these variables u and k minus is centered at the sample average. There's a small near the boundaries. And having in mind that is approximately Brownian bridge, really standardizing would mean that we take the square root of t times 1 minus t. That would standardize the Brownian bridge. But the issue is that then the Brownian bridge divided by this square root standardization is not almost surely finite random variable. And so it is commonly used then that one uses weights, in a weight function j, yes, which is greater than something for which this still is true, so that everything is well defined, yes? And so we get here a beta parameter which has to be strictly less than 1/2. Okay, and then we again standardize the weighted Q-sum by an estimate of the asymptotic variance. And now we have to simulate the quantile function here. So the supremum of Brownian bridge with this weight function, but this is not a difficult thing. So it very easily, so 10 lines of R code. The estimation of the change point is simply done by, using the k where the Q-sum statistic is maximized. This is a quite common approach. And the multivariate Q-sum transform is now as follows. So suppose we have L-weighted Q-sum. So we take capital L pairs of weighting vectors v and w to look into our covariance matrix. For example, to consider contrast or whatever. And so in terms of a testing problem, this means that we want to test that we have no change with respect to these projections against the alternative that induced by change point where the covariance matrices change and assuming that the projections are appropriately selected, that there exists at least one bilinear form where a change is visible. The approximation, actually, indeed, I will show you later the result, allows for the case that L tends to infinity. Yeah? So it's not necessarily fixed, yeah? the number of projections. And the global test, if you want to have this kind of global test, can be formed as a quadratic form in terms of these multivariate capital L projections. I will not discuss this so closely because I think this is not what will be is really the method of choice if you have if L is large. However, it can be done. The choice of the weighting vectors, of course, is a question. It depends, of course, on the concrete application. We can use binary vectors if you want to analyze some subsets of the covariance. We can use sparse principal components estimated from a learning sample as are motivated. We can take it from a known basis, of course, as well. Yeah, so, but if you have an unhappy choice, then a change, of course, is not detectable. This is clear. And the classical solution used in many fields of science is then to use a random projection. So this is nothing which is really new. And one can have in mind the Johnson-Lindenstrauss theorem, which tells us that if we have endpoints in a high-dimensional space, they can be embedded into a low-dimensional space and the dimensions of this order, such that their distances is preserved up to a given accuracy with a high probability, and you can in advance say how accurate this should be. Okay, so the asymptotics under the change point model works as follows, generalizes the existing results we already published. So here I look at the bivariate process now. Here I consider time series which are first induced by the coefficients before the change point, and here is the time series induced after the change point. The idea is to work out the asymptotic approximations, yes, for this guy. Then if you have the change point, then yes, in the asymptotic and in the approximation, you switch from first component, which gives you the approximation before the change point, and then you switch to the second coordinate here, which gives you the time series after the change point. Okay. And so technically one can work as follows. One derives a martingale approximation of the D and K, and then one can work out that the conditional variances of these martingales are approximately in the L1 sense to quantities which can be computed from the coefficients of the time series, which are here generally denoted by this A array. And the asymptotic covariance are the same way, can be derived, and they are asymptotically equivalent to quantities which can be computed from your time series model. These guys are now used to set up a Gaussian process, 2 dimensions here, which has exactly these quantities as variances and as the covariance. Okay, and the summary of the theory is as follows. So if we have LQ assumption on the weighting vectors, so if you do not standardize, the theory needs that it is on one bounded uniformly in the sample size. Then we can approximate the Gaussian, the Q-sum statistic using weight function G by this Gaussian process. So the maximum of this Gaussian process, here's a bridge process, and here a drift term enters. This is from previous slides where the expectation has been computed. Here, this gives us the drift term, and then we take here the maximum over this process. Then if we standardize the Gn with the right asymptotic variance, then it follows that for any ratio consistent and homogeneous estimator of the asymptotic variance, we get this approximation in the little op of 1 cent. of the statistics we really use if we do statistics. Provided that these areas, these quantities giving the right asymptotic variances and covariances between the martingales, and therefore also because the martingales are approximating between the statistics as themselves, then we can also have a central limit theorem, so this is quite nice. And here you see then the asymptotic expression of the drift term. If you look at somewhat closer at the expression of the drift term, then you can of course formulate assumptions when this drift term is vanishing asymptotically. And in such a situation, we cannot detect the change asymptotically, yes, even if the sample size is increasing. And if this drift term expression diverges, then of course we get a very nice result and we have power. And cases where this converges to some function, not depending on n, then we get situations where we have some kind of local limit theorem, yes, we have a non-generated asymptotic limit where the drift term enters in the limiting expression, providing power. For example, if we look at a change point model of this type, so delta n is the difference, and suppose that this converges, so here the rate of convergence is 1 over square root of n. Suppose also that this limit of this bilinear form exists, and if you write down the spectral representation of delta n, the difference between the covariance matrices, then of course it is clear that the change in the drift is maximized if we select the weighting vectors as leading eigenvectors of the difference of the covariance matrices. For example, if we have a spike covariance model and after the change, a new spike arises in our model, then of course the change is detectable if the weighting vectors are not orthogonal to the new spike. In a sense, yes, orthogonal to the eigenvector corresponding to the new spike. The moderate version can be also approximated. So we have our pairs of projections, and now the covariance parameters arise between the Q-sum statistics for two pairs of weighting vectors and an array of coefficients before the change and an array of coefficients after the change. And so here are again written down the Q-sum statistics we want to approximate, so the non-standardized version. And the summary for the unweighted case is that we can define an L-dimensional Gaussian bridge process with a covariance matrix given by these quantities I showed you on the previous slide, such that our statistic vector of our multivariate vector of Q-sum statistics can be approximated by the vector of these maxima over these Gaussian processes, where here we have a bridge process, here again we have a drift term. And in the case that the number of these Q-sum statistics, L, diverges, so converges to infinity, in this situation one needs an additional scaling with 1 over square root of L. Yes, this is what turns out. It also works for weighted Q-sum statistics, but the result is weaker. Yes, we have to use the law of the iterated logarithm in order to estimate the boundaries, yes, the weight function, so there's some care has to be taken. But however, one gets the validity and can justify the procedures in this sense. So we have a kind of weak approximation result, and this is uniform over the J indexing the Q-sum statistics. The change point estimator is also consistent, which is quite easy to prove using the martingale approximations. This is quite nice, and the conditions on the weighting function are also somewhat weaker. I will not discuss this in detail. Let me discuss a little bit the estimation of the asymptotic variance. We have this situation that we may have a learning sample, and we can also use it to estimate these asymptotic variances. Then we have here our sample. Here we have the estimated change point, and so this is the fraction of the sample after the estimated sample change point. And we can use also instead of the learning sample for estimation, the in-sample estimator, ignoring that there could be a change point. And we could also use simply the observations until the estimated change point. And so we use a Bartlett type Longhorns estimator, yes, for the product of the projected time series. This works and estimates the right object. And this can be generalized to the case that we want to estimate the covariances between Q-sums corresponding to different weighting vectors, which is needed for the multivariate situation. So we have here different pairs of weighting vectors and use the corresponding covariance estimators at the right legs and form then the Longhorns estimator. And the result is that under some technical conditions, the estimator converges to a convex combination of the quantity before the change and after the change. So this is, of course, then not consistent if you have a change point in the sample. Then the idea is to use to study a sequential version of this estimator. And if you have consistency for the sequential version of the estimator uniformly in the sample size, then you can combine this with a consistent estimator of the change point in order to use only the data until, where you have evidence that this is really before the change. Yes, so here now all estimators for the Longhorns estimator are also only calculated until sample number n times u is between 0 and 1. This sequential Longhorns estimator is consistent, and we can then combine this with a consistent estimator of the change point, and we have one in our situation. And this is what I call the stopped sample estimator. Yeah, and then you get an consistent estimator. I will skip a little bit the application, but actually it turns out that if you use a sparse PCA, you get quite nice result. You can get, although we only look here into the second order structure, yes. So this data is mean corrected. Yes? So the averages are really 0. You get a kind of segmentation of your monitoring stations which correspond to geographical areas. So very nice interpretation. And if you apply the test statistics, here the unweighted case, you get in most cases no significant result, which is right. Why should there be a change? But in some cases we get the null hypothesis is rejected, so this would correspond to situations where one could perhaps discuss with people who are really working with such data on a daily basis. What is the reason that there is a change? There can be changes, for example, local climate changes, new industries with more pollution or whatever. If you have the weighted change point test, you get much more rejections. And if you look at the estimated change points, these more rejections are usually at the beginning of the sample. The weights are actually indeed introduced in order to get more power if a change is right at the beginning of the sample. But you also get quite a lot of rejections right at the end of the sample. I'm not sure whether these are correct. I have no time to discuss the simulations in detail, but it turns out that the things work quite nice. The unweighted Q-sum test is better than expected. Of course, the weighted Q-sum, where the beta is selected at 0.45, has more power at the beginning. So if the change occurs right at the beginning of the sample, then this test is much better in terms of power. But if it's in the middle of the sample, then the unweighted Q-sum is better. And so we only have really an advantage if the change is right at the beginning of the sample. Okay, so let me conclude. I discussed procedures for testing and estimating changes in covariance matrices, especially the results apply to Warmer models and a class of spiked covariance models. The high-dimensional framework allows that the dimension grows to infinity with an arbitrary rate. There's no constraint, especially there's no need to assume something that's only proportional to the sample size or grows exponentially or so. The detection is done with Q-sum statistics, which are known to work very well. The results also hold for multivariate Q-sum and the global test. And the asymptotics is worked out really under a change point test. We can estimate the change point consistently, and we have actually 3 proposals for estimating the asymptotic variance. And here in this situation, this works. So from the simulations and applications, there's no hint that that one should not do this. So the results are okay, are very good, I think. Thank you so much.
This one here. Okay, so thanks to the organizers for organizing this wonderful workshop here, and thanks to the scientific committee, in my case Lajos, for proposing me as a speaker. I'm not really working recently in change point problems, and I forgot that I had a paper on testing for Gaussianity and functional time series, which would have been a goodness of fit paper, so I proposed something else which I thought would be the closest for the moment. And this is for testing for periodicities. So kind of when you think of a change point, then you test for like that the mean changes once or several times, and here this would be like the mean changes like periodically somehow. It's close enough, I would say. This is joint work with my former PhD student, Clément Servecki, and my former postdoc, Vaidotas Karatseos. Now Clément finished, Vaidotas left to Davis, and I left to Graz, so we didn't really have time to write up the paper, finally. And so results are there. It's written up, but not polished yet. Okay, so we had a few talks about functional data and functional time series. I give just one more example. This is my favorite data, is PM10 from Graz, okay, pollution levels. So this is fine dust particles. And I plot the trajectory over 10 days here, okay. So this is the data generating process is a continuous time process. Of course, everything is measured in discrete time. So we have here 30 minutes resolution. And so this gives you a continuous time process in principle. And since we would like to do statistics, it's often more convenient to have like repetitions, right? To have a sample. And one way you can get a sample from this continuous time process is like that you, with multiple observations, if you cut this process into pieces, like daily data, okay, and then you have a sample of 10 curves. Each day is one curve. And since this is collected sequentially of a functional time series, okay, so the time series I'm referring to is discrete time series, but the observations are continuous time observations, okay? And these continuous time observations, they will have a structure, like they have a diurnal structure, okay? So usually pollution levels are higher during the rush hours, lower during the night shifts. So you have already like a periodicity in this respect. Okay, but I would like to look for a different type of periodicity, namely in the discrete time parameter. So what I did here, I plot this PM and also some other pollutant, nitrogen monoxide, okay? So I had a sample of these curves now for like one winter season. I think we had like 180 data or something like that. And I take all the Monday curves and average them. So for the PM, this is the black curve, okay? Then you get this Monday mean curve. You get the Tuesday mean curve and so on. And the question now is whether there is a periodicity here. So is this like is this constant over the days, over the weekdays, or is it changing? Okay. And by just looking at the plot, you will probably notice that on a Sunday we have maybe just only one peak, or also on the Saturdays we have lower peaks and higher low values. So, well, and the data are relatively noisy. So just by looking at the plot like this here, this is not very reliable. And so we would like to come up with some kind of a test, okay, statistical test. And well, in our first paper, this I will only just briefly mention here, we had like all kind of different models, but I'm showing you now kind of a general model. Okay, this would be of this type here. So we have our data, YTU. So this is the, let's say, the pollution level on day T at intraday time U. And so T is discrete and U is continuous, usually between 0 and 1, let's say. And under the null, this is like just a stationary process, okay? So I'm assuming that this is a mean curve, mu u, and like a noise process, ZTU. So ZT is functional white noise, or some kind of a stationary functional process, okay? We will consider two situations actually later on. So the more interesting stuff is, of course, if this is a stationary dependent process. And then if there is, if there's, the process is stationary, that's the model, but if you would like to somehow consider something periodic, there is also this curve or this direction WTU, which is T periodic in the discrete time parameter, okay? So in our case, we would have here that the little d is 7, and so like every 7th day we have like the same kind of mean curve. On Mondays we have a certain pattern, Tuesdays we have a certain pattern, and so on. This is the idea there. And for identification reasons, we assume that this W's add up to 0. So you're basically in a very simple, it's functional, so it's a little bit more complicated, but in principle, this is a very simple 1 factorial design. Okay, so this is the classical ANOVA problem, actually, what we are studying here. Despite the fact that we would like to assume that this ZT is maybe a dependent process. This makes the thing a little bit more complicated. And there's two things that we should somehow look at. So the first thing is, two general settings. The first setting is when the period D is known. This was a first paper which is already published. I will just mention one result, but I will not focus so much on this one here. And then one of the referees said, but what is if D is unknown? Okay, then I would, if I were an applied statistician, I would say then I would do nothing, because then maybe you should not test for that. But from a theoretical point of view, it's also interesting to see what you can do if nothing is known. So then you have to estimate the D as well. This makes the story a little bit more complicated, okay? And this is what I will focus on in this paper, in this talk now, okay? And one of the things that I would like to also stress is that for both settings, we were actually interested in obtaining fully functional tests. Okay, many tests that people do in functional data analysis are based on, so you project on a database, on a basis, some basis curves, principal components or something like this, and you make a multivariate version out of it. Okay, so here we would like to stay fully functional, and I give you one example where you can see that this is kind of a more natural approach, and it's yeah. Well, okay, so let's assume that the period is known, like in the example that I've shown you. Okay, I would like to test for weekly periodicity. So my D in this case would be 7. Then the very natural statistic would be just this ANOVA type statistic. Okay, we are computing here, so the YK bars are, let's say when K is 1, this is all the Monday mean curves. Y2 bar would be the Tuesday mean curve, and so on. And we compare this to the grand mean, and we take this L2 distance, okay? And so if there is, if all days, like all weekdays have the same structure, then in this case, this should be small. And if there is like a pattern, then this should be somehow large, okay? And the question is what is large and what is small, so we would like to have like a distribution for that. Okay, so this was one of the statistics that we considered in the first paper. I think this is the most interesting in some sense, so therefore I show you what is the result there. I would like to note that this is, if we would have just IID noise, then this is well known actually. So the functional ANOVA is known then in this case, but it's more complicated if you have dependent noise, because this Y1 bar, so the Monday mean curve and the Tuesday mean curve, the estimated ones, they are relatively correlated. Okay, so you have a complicated correlation. And the first thing that we did, we were looking what do people do when they do ANOVA for dependent data. And what usually is assumed is that within the groups, okay, so within the Mondays, let's say, you would have dependence, but you have independence between the groups. So my Mondays should be independent from the Tuesdays, and here it's just the opposite, right? Mondays and Tuesdays will be correlated, and Mondays probably are almost independent because they're separated somehow, so it's kind of a different situation here, okay? And so this is what you get if you work out the asymptotics. So our functional, this is all up to scaling. I'm not very precise in my slides, okay? So this functional ANOVA statistic, what you have seen in the previous slide, converges under the null, so that if we have no periodic pattern, and if you assume some kind of a weak dependence, which is quite general, then this converges to a sum of these variables psi k, which are described here. I will come back to this. And so we have a sum of independent variables psi k, and we have d minus 1 over 2 summands. These, let's say my example, it's 7, so d minus 1 is 3. d minus 1 is 6, and d minus 1/2 is 3. Okay, so if you have an odd or even number, there's different outcomes. And so does psi k have an interesting form? There's what's called a hypoexponential variable. Okay, so this is a weighted sum of IID exponentials, and the weights is an infinite sum here, and the weights are the eigenvalues of the spectral density operator. Okay, so the spectral density operator is just a Fourier transform of the lag covariances, and this is like a covariance operator. Okay, so it's a positive definite operator. And so if you look at this operator so this is indexed by this frequency theta. If you choose the frequencies, these fundamental frequencies 2 pi k over d, then you compute the eigenvalues. These are the weights in there. So this is quite I would say, a nice result, Okay, and this also works practically quite well. I show you here just one evaluation, okay, which somehow emphasizes that it's good to work in a fully functional setting. So what you see, again, is I took this NO data, okay, and it's clear from the data that there will be a periodic pattern, okay. We know that also because this depends on the traffic and so on, and traffic is not constant over the days of the week. So we did a test whether we have this periodicity or not, and so what is coming out from the fully functional test when we do this functional ANOVA is a p-value of 0.06, so which gives high evidence that there's periodicity, okay. So what you could do is you could do now the classical, let's say, functional data approach. You project everything onto a basis and you run a multivariate test, also adapted for this dependence, okay, that we have to take into account, or that we wanted to take into account here. And the simplest projection is you project just on the constant 1, in which case you just compute daily averages, right? So this would be just the daily averages of the PM10 data. And I have a scalar sequence now, and I run this periodicity test for the scalar sequence. And then I get a p-value of 0.1 approximately. Okay, so it's not very high significant, or maybe usually we test on a 5% level. We would not consider this as significant. If you project on one principal component, which explains 68% of the variance, then you would have a p-value of 0.07, which is also not too small yet, so still not very high indication of periodicity. Then if you project on two principal components and run the multivariate version of that, you get a p-value of 0.17. Okay, this explains 81% of the variance. So Piotr said yesterday that in functional data, usually the applied people would say 85% of the variance should be explained, okay? So we would have to add one more component. Then you have like 3 principal components, and then all of a sudden you see that this is extremely highly significant, okay? But so this 85% rule is new. In our last paper, we said 80%. So it depends on what you choose, yeah? Okay, so either it's absolutely not significant or highly significant, okay? And it's just because I think that this periodic direction that was somehow in the background was hidden in the 3rd principal component, okay? And just what I want to say is that if you do this like multivariate approximation, it depends very much on the basis that you choose, okay? If you project here in the first 2 principal components, basically these principal components are orthogonal to this periodic pattern, and therefore you do not detect anything here. So with a fully functional test, you are on the safer side, although, of course, it's at the price of some power. Good. So I would like to come now to this main part of this talk here, which is about when the period D is not known, okay? And previously, we would know that we would like to test for length of the period is 7 days or something like this, but now so you have just arbitrary functional data and a time series, and you would like to know whether there's an unknown and hidden periodicity there. In this case, so what we have done so far, we allow only for IID noise. Okay, this is quite restrictive, of course, but it's still complicated enough there already, and somebody maybe in the audience can extend that if anybody's interested. Okay, so we consider again a fully functional test, and this is now a very classical kind of approach. I mean, it's very parallel to what you would do in the scalar time series setting. So we take basically the maximum periodogram. So this dn here is the discrete Fourier transform of my functional data. And this discrete Fourier transform is basically, if you're not so much working with this stuff here, it's basically computing a correlation between my observations and a sinusoid. Okay? So if this yt also is like behaving like a sinusoid at certain frequency, then this should be somehow highly correlated. I mean, it's not really correlation, it's an empirical kind of correlation with a deterministic function, but you will have a spike, let's say, at the position where there's a frequency, okay, where there's a periodicity, at the frequency where you find a periodicity. And so what you do now is you look at this object here, and since it's functional, we compute its square norm, okay? This is kind of the functional periodogram now, and we look at the maximum over all fundamental frequencies, it's called. So this is 2 pi j over n, where the j is running between 1 and n half, more or less. Okay, depends again if this is odd or even, but let's suppose now that n is odd, even. Okay, so in the scalar setting, this is a well-known object, and in the scalar setting, then if you would have that under the null hypothesis that there is no periodicity, that this Mn, so this maximum value of the periodogram, appropriately centered, converges to a Gumbel distribution. Okay, this is not surprising. So this is an extreme value distribution. We're looking at the maximum of a sequence of statistics, so it's converging to a Gumbel. And let me give you, I mean, many of you probably know that result anyway, but it's a simple explanation. So if your data are Gaussian, then you see here that actually the statistic, I mean, you have a weighted sum of Gaussians, again Gaussian, okay, so you have Gaussian variables across the different frequencies. And because of this trigonometric functions being orthogonal, somehow this become uncorrelated, so they become independent Gaussians. And if you square independent Gaussians, you get chi-square variables. And since you have real and complex part, you get two chi-square variables. And if you add two chi-square variables, you get an exponential variable. That's basically the explanation for that. Okay, so that's kind of trivial. This is you will find in any textbook that if you have IID scalar data, then this thing here is just IID exponential variables. Okay, and so that the extreme value, the simplest extreme value you can find is the maximum of IID exponentials. Okay, this is converging to a Gumbel. Now, without Gaussianity, this is surprisingly more complicated. Because without Gaussianity, it's easy to have this discrete Fourier transforms. You see, this is like a partial sum, weighted partial sum. Okay, so the central limit theorem will hold under IID assumption. So for every fixed frequency, this is becoming normal. And if you choose like a subset of frequencies, which is finite dimensional, so a finite fixed number of frequencies, this is also becoming like normal. Okay, so you can easily prove with the central limit theorem that if you take this discrete Fourier transform, so this periodogram squares here, at a fixed number of frequencies m, so j1 to jm, theta j1 to theta jm, this will be also like distributed like IID exponentials. But here the situation is more complicated because we have a growing number of frequencies, right? So we have this number, the number of frequencies here, the theta j's here, there are q of them, which is n half. So we have it's proportional to our sample size. So we would need a central limit theorem where the number of observations somehow is as big as the number as the dimension. Okay, the dimension is the same as the number of observations, and so that you cannot just trivially go ahead here. And I was quite surprised when I worked on that only it was Davis and Mikos in 1999 who obtained this result for IID sequences when you have 2 plus epsilon moments or something like that. Okay, so this is an annals of probability paper. This is I would say relatively reason for this very simple result, or this not simple result, but for this relatively simple statement here. This was later extended. And so what we wanted to do, we wanted to extend this kind of result here to the functional setting, okay? And so we were looking what did Davis and Mikos do, and we would try to imitate their proof and first generalize to the multivariate. This was the exercise for my students, okay? And then we saw that this is actually quite complicated. They used all kind of approximation results by Einmal and so on, and we were not really very successful in extending that to the multivariate. So we had to come up with a different idea. And okay, so these were basically the results that we got. So first let me say, so the multivariate, I mean, we wanted to work on functional data. You can make your functional data always multivariate by projecting them on the basis again. Okay, so that's what we did first. So we said, okay, remember that dn was our discrete Fourier transform, so square root 1 over square root n, sum of yt times e to the I t theta. And those yt you can, by a Cahunen-Loew expansion, always approximate like with a p-dimensional version. Okay, so you project on your eigenfunctions, and so this would be a p-dimensional version of my yt. And if my p is large, this will be approximately yt. Okay, but then I'm in finite dimension with this dnp here. Still functional, but finite dimensional functional. And so the first thing that we showed is that this finite dimensional functional thing, if you appropriately standardize it, will converge again to a Gumbel distribution. So this is kind of the multivariate extension of Davis and Mikos. Okay. Then in the second step, this is the main step, we were letting this dimension grow. So we can allow for sequences Pn that go to infinity, so this approximation parameter Pn, this is the dimension in which we project, grow with the sample size, and this is again converging to a Gumbel distribution. Okay, so this was our main result, I would say. And from that, you can somehow come to the fully functional setting, where this Mn, so the maximum over the periodograms, appropriately standardized, will really converge to a Gumbel. Okay. And I will avoid here the technical conditions, but I will somehow try to explain now how this worked, okay? Good. So, again, remember what my Mn here is. So our Mn, so we have this discrete Fourier transforms, okay? So this is the weighted sum of our data with these trigonometric functions here. We have different frequencies. we take the norm of this object or the square norm of this object, and then we look at the maximum over a set of dense frequencies, okay, 2 pi j over n or something like that. Good, so this is our mn is the maximum over these guys here, and that we would like to get the asymptotics. Okay, so the first thing is when we wanted to prove the fully functional, so this was the theorem 3, okay, we are going to assume that this lambda, which was the scaling, this is just the largest eigenvalue of my covariance operator underlying the noise. I assume that this is 1, okay, to have a simpler notation here. And then I'm interested in mn minus bn, so this is the maximum with the correct centering constant. And of course, trivially, you can decompose it in such a term here. Remember, this MNP was the same maximum, but now when we have projected our data on p dimensions, okay? Our raw data were projected onto the first p principal components, okay? So this gives you a very nice approximation here. Okay, so then you would like to show that this is converging to a Gumbel distribution. So we have 3 terms here. I'm proving that 2 of these terms converge to 0. So the third term is trivial, okay? This is just a constant. I mean, you can just write it down as you will see this is converging to 0 if my p goes to infinity. Okay, so I'm assuming now that my dimension goes to infinity. This is trivially converging to 0. Then you have the first term, so you have this mn, so this is the maximum of the true functional periodogram, and then mnp is the maximum of the functional periodogram when you use approximated. So when you approximate your functional data by principal component analysis. And again, you can imagine that if I choose my approximation very well, meaning that I choose a very large p, then this should also become here somehow small. That's also somehow technical work, okay? So if I let my p grow fast enough, the approximation with the Kahn-Loew expansion will be good enough so that the maximum of the original functional data is the maximum of the approximated functional data. Okay? So for fast enough growing p, this guy here will be also small and go to 0 in probability. So then you have to study only this guy here. So this is kind of the multivariate version with growing dimension. Okay? This is what we have to take care of. And here, of course, we have now a little bit of a challenge that this dimension has to grow. And by the first thing, we have to let the dimension grow fast enough. But if the dimension grows fast, you have very high dimension. So here in the second, actually, you want to let the dimension grow slow enough. Okay, so you have to be careful that there is an intersection in the end between these these things. Okay, good. So this is the challenging part, and let me try to explain this guy here. Okay, so we're looking at this maximum periodogram when we have like growing dimension. Okay, and if you write this down, I mean, this is not very complicated, actually, what we are doing. So I would like to compute the probability that MNP is less than x. I would like to have the distribution of this thing here, right? So MNP less than x, if you write it out like on a piece of paper, you will notice that this is basically something of the form, the partial sum of vectors, of n vectors, being in a set A, where these vectors have this form here. So these are my yt, are my functional data. Then I project these functional data on these principal components, so V1 to Vp, and I multiply with these trigonometric weights here, okay? So cosines and sines at the different frequencies theta I, okay? Theta I is 2 pi I over n. And you see that these yt's here are actually np-dimensional vectors. So kind of what I need is an np-dimensional, a central limit theorem for np-dimensional vectors. And I need not just a central limit theorem, I need this whole thing with a rate. That's kind of what it boils down to, okay? This is the problem. So n is already big. So if my p is 1, if I'm just using the result of Davis and Mikosh, where they just work in the scalar setting, my dimension is n. And if I have now a multivariate version, I have np. And if I have a multivariate version where the dimension goes to infinity, I have np with p to infinity, okay? So my sample size, if I take the ratio between the dimension and the sample size, it's going to infinity. Okay, so we are in a complicated situation somehow, or in a difficult situation. Okay, what will be interesting? What is this set A here? Okay, so we have to set that this is in a set A. This depends, of course, on X, but as you will see now, this set A is not very complicated. This is the good thing. Okay, so what we need is a Gaussian approximation, and so what we will need, what is kind of the key result that you need there, is something like this here. You would like to compute the probability that this partial sum in A, which has said that this is the same thing as MNP less than X, okay? You would like to compare this with the probability of a partial sum being in A, where now this partial sum is exactly the same partial sum as before, but just that I replaced my IID functional data with IID Gaussian functional data, which have the same moment structure, Okay, so the same covariance basically. So they have the same eigenfunctions. Why do I want to do that? I want to do that because this thing here is just exactly this thing here, but now if my data were Gaussian, and as I show you in the scalar setting, if your data are Gaussian, everything is kind of simple. Okay, this is relatively simple. You can give it to somebody who is familiar with the Gaussian distribution, and you can just prove that. Okay, so this is so to say, if I would be able to replace my vectors here with Gaussian vectors, everything is simple. So I need to know that this thing here is somehow small. Okay, so we went to the literature to see if we can do anything about there, and then we were seeing those results of Bendkus and so on. These are all kind of optimal results and very, very difficult things. And it turns out that those results are not usable here. They're not usable here because, so for example, if you take this class of A, so you need to take the supremum of the set A, a class of A in A, okay? A is a class of sets. If you take, for example, Euclidean balls or convex Borel sets, then the maximum dimension that is allowed is of the order n to a third or n to the 7th, okay? That's all kind of results. But nothing goes up to n. We need actually much bigger than n, okay? And here we have much smaller than n. So we cannot, this is kind of a Berry-Esseen theorem for high dimensional, but it's not going high enough for what we need, okay? The good thing though is, so we found a paper, a recent one, by Januzukov, Chedverikov, and Kato, which works in very, very high dimension. And it works in very high dimension because those guys restrict to very, very simple sets, a very, very simple class of sets, A, okay? I'm not going into all Euclidean balls or all convex Borel sets, but what they were considering, among others, they looked at different things, at so-called S-sparsely convex sets, okay? Whatever that is now. This is a very simple class of convex sets. And what turns out to be the case is that in our setting, okay, this class of sets A that we need to consider here are 2p sparsely convex sets. These are 2p sparsely convex sets. So we have their result, basically we can apply it when S is 2p. And so if you do that, so if p is fixed, we can directly use their result and we are done. So we can reprove this Davis-Mikush thing when p is 1, like in 2 lines now, with this result. Okay, so this is, I mean, not 2 lines, but from here it's a very simple consequence somehow to prove a multivariate version of this Davis-Mikush result or to reprove their paper. Okay, but we have a very strong machinery here, which is coming from this paper, which is, I think, also annals of probability or something like that. There was an additional difficulty. Now we want to go to the functional setting. Okay, so we have to let our p grow, and that paper is very complicated. I cannot say that I understand it, but we were trying to trace down the following thing. So they assume that S is fixed, so this S sparsely convex sets, the S is fixed, and so what they get in their approximation rate is something that depends on the S. But they give not an explicit constant on how it depends on the S. And since now my S is growing, I need to somehow work out this constant on our own, okay? And luckily we had this guy Kato who would help us here a little bit, okay? So it comes down to kind of some concentration inequality, and there we could see where this is somehow coming up. And so finally what we did with some extra work, we could somehow compute also this constant depending on S, and so this is what we got here. So remember the rho n p was this approximation error here, and the rho n p is of the order p to the third log n, so n is the sample size, p is the dimension of the approximation, and then we have here divided by lambda p a half. Okay, lambda p is the pth largest eigenvalue of my covariance operator, which tends to 0. So as Professor Stute said yesterday, so these eigenvalues are your enemies if they are small, okay, and they are small eigenvalues. So this p is, lambda p goes always to 0, okay, so and if it goes fast to 0, like in the exponential case, this can be quite a big constant here. Anyway, so now we had to work out some special cases, okay, and I can show you 2 results. So for example, our fully functional result holds if the eigenvalues are basically decaying exponentially, and you have more than 6 moments. In this case, you can choose Pn, so the dimension of order log n, and everything would work. So then you have fast enough approximation so that the manipulated data would behave like the original data, and at the same time, the dimension is not growing so fast that you would lose somehow this central limit theorem, okay? And if you have polynomial decay rate, then we need just higher order moments, okay? So the number of moments then gets like, you see, the closer you are here with nu to 1, the higher moments you need somehow. Okay, my time is almost up, so I will just conclude here. So consider a functional time series with unknown periodicity and some IID noise in H. From the previous results, we can conclude that our test statistics, so the maximum periodogram, the fully functional one, appropriately standardized, converges to a Gumbel distribution. And on the other hand, if somehow there is periodicity underlying, then this T here will converge with probability 1 to infinity. Okay, so we have a consistent, asymptotically consistent test. I have also some kind of a data illustration. I'm going to skip that, just showing that this is basically working. Okay, so we have generated realistic data. We bootstrapped from this PM10 curves, and we added some kind of a periodic function. And it turns out, so if you have small sample sizes, I mean, this is just different kind of periodicities, but unknown periodicities. And you see here basically the power. Okay, so when you have a sample size 500, the power is basically approaching 1. This is under the null, by the way. So you see also that the level is kept quite well. Okay, that's it. So we have proposed fully functional tests for periodicity in the first paper when the period is known. This paper is published. And the second paper when we do not know the periodicity. In the second paper, we have to focus on a very simple setting where we have just IID innovations. In the first one, we can allow for general dependence. And yeah, so the asymptotics is kind of challenging, but not if you have very smart guys like Jeno Zukov who have published some nice results that we can use here. Thanks for attending the talk. I also go. Yeah, it's good. It's good.
Let's see how I get this going. Can someone help me to get started here? Let's see. Okay. Escape. Okay.
Keep it here. Which one?
Okay, the asymptotic. Yes.
This one?
Thank you. Okay, I'd like to start off by thanking the organizers, Emanuele and others for this nice workshop. And my talk is going to be of a slightly different flavor. And the title says asymptotically efficient estimators based on spacings. And there's a rough outline of what I'm going to do. And in fact, there's quite a bit of goodness of fit testing, but I'm not going to focus on that today. So in spite of the short time that I have, I'm going to give a brief review, introduction review of this area, because this is not something that's familiar to all of us. And then I'll go on to a special paper that we recently wrote and is come out in journal Test. Okay, so testing and estimating are two of the aspects that, well, it's a bit tricky here, but we'll manage. Okay, so what happened? Did I switch some lights there? I didn't do that, did I? Okay. Okay. Good. Okay. Okay. Now, maybe I need to be there so I can read this. Okay. So you see, I start with the n-1 observations on the rail line, and from a continuous distribution, I said, and then I look at what are called simple one-step spacings. I'll increase that 1 to a larger number later. These are just the gaps between successive observations, and they play a crucial role in terms of directional data about which we had heard two talks yesterday. In the case of a two-dimensional directions on the unit circle, it turns out the origin is arbitrary and is immaterial. So the gaps between points play a pivotal role. They are in fact the maximal invariant. So anything you do on the circular data analysis has to be based on these so-called spacings. That was my motivation to get into spacings. And then I do tests of hypothesis, inference of both types. Testing, estimation can be done based on these spacings. And I'll give you a brief review, as I said in the beginning. So you want to test a null hypothesis, the usual goodness of fit, that F is a given distribution, F naught, fully specified at this point. One can generalize these ideas much more unknown, complex, composite hypothesis and to multivariate cases and so on, but let's stay simple. Okay, so F is F naught. So apply the F naught to all the data and then call them yi's. So the null hypothesis that F is F naught corresponds to now testing if the yi's follow a uniform distribution. So look at this y1, y2, yn. Now you see why I picked the n minus 1 observations. So I take 0 to be the y naught. These are the order statistics of the y values. Okay, y naught is my 0, yn is arbitrarily defined to be a 1. So these are the ordered values. And then the gaps between these observations, successive observations, yi minus 1, those are the so-called spacings. So if you start with n minus 1 observations, you get the n gaps. In other words, these n minus 1 points split the interval 0, 1 into n parts. And this is the same thing with, for example, in the circle, if you have n observations on the circle, they end up making you n spacings. So they have the same properties. And so if you have these null hypotheses, let me specifically call them TIs, uniform spacings TI. DI is my more general notation. These TIs, very simple to play this game. This joint distribution of TIs is a Dirichlet with 1, 1, 1, 1, and then the expected values and covariances. And one of the interesting points to note is that n times TI it goes to an exponential distribution. That if TI is obviously as n becomes large, TIs go to 0 in probability, but n times TI goes to an exponential distribution. In fact, there is an intimate connection to exponential distribution and the uniform spacings. The TIs have the same distribution as the WIs, or the summation of WI, where WIs are exponential theta, IID. Or, other way around, you can also write the TIs as WIs conditioned on the fact that the summation of WI is a 1. Okay? These uniform spacings are related to the inter-arrival times of a Poisson process, and there are a lot of interesting connections to exponentiality. So when you want to test goodness of it, about which I'll talk briefly, there are 3 broad classes of tests. The chi-square test, about which people talk, the empirical distribution function-based tests, which is all over the place, and then those tests based on spacings. And that is the third class of tests that get mostly ignored, and that's what I will tell you a little bit about. And then there are, of course, many other ad hoc tests. Like testing exponentiality, you find dozens and dozens of tests for that. Now, for doing this testing of goodness of it, a general class of tests can be expressed in the form h of NDI. H is a convex function. This is a typical statistic. And there's a nice review paper by Pike going all the way back to 1965 that is perhaps worth to read. And here are potential classes of H functions that Hx is minus log x. That leads to what's called the maximum product of spacings. If you have Hx is minus log x, that that corresponds to the product of the spacings, right? And then the Keil divergence measure. Or, for example, this Hx is absolute x minus 1, and that leads to a statistic like, xi. What's going on? Okay.
So di minus 1 over n. This has been sometimes called the Rao spacings test, and I was known as a Rao at one time. Okay. In any case, h of x can be any of these power functions, and there are a whole class of tests of this kind. I'd like to take a sip of water here. All right. 9-hour jet lag that I'm still overcoming. Okay. Okay. So there's a broad class of tests that one can talk about in testing goodness of fit. All these are tests for testing F is F naught, after having converted them into uniform, order statistics, spacings, and so on. So there are a lot of, question is, these are dependent variables, di's and ti's. So the question is, what is the distribution, asymptotic distribution or exact distribution of statistics Sn? And there is a whole bunch of possible approaches. People have used characteristic functions, conditional approaches, conditional meaning. Ti's are like wi's conditioned on the summation of wi being 1. So conditional approaches. And so we at some point gave a general approach that says, let's look at the empirical distribution function of what we call normalized spacings, this capital H and X function. And then you can write any statistic Sn, look at the line below, or last line, and that can be written as a functional of the Hn of X. And then you might be able to get, in fact, the distributions of any of these statistics using this approach, using the empirical distribution function of the normalized spacings. And here is a typical result. If we take uniform spacings, and that theorem says that h of ntk minus expected value of h of w. What is our w? W is our exponential one random variable, the simplest variable that you can think of. So that is the mean, this is the variance of such statistics h. Okay, that's a typical result. And the question is, what is a good h? And it turns out h of x is x squared, has the highest Pitman efficiency, and hx is log x, has the largest Bahadur efficiency. I won't get into any detail here, but there's a book I'm attempting to write. This is going to, be containing a lot of this kind of results about spacings and so on. But in any case, I'll skip that part of testing of hypothesis. The estimation, we usually use the maximum likelihood estimate based on that L theta. Okay, so that's typical. And it turns out maximum likelihood estimates have deficiencies. Sometimes the likelihood may go to infinity, like in the case of normal mixtures. Or, for example, the densities may not be available, like in stable families. And in fact, there's a nice paper by Bahadur, and like Niemann-Scott example and other examples that show the MLEs may not be consistent. So there are issues with MLEs. So we suggest an alternate approach for estimating unknown parameters using the spacings. Okay, what's our approach? Okay, let the x1, x2, xn minus 1, these are the order statistics, and f is these come from a distribution with an unknown parameter. It could be a vector, f theta. So apply the f theta x to x0, x1, and xn, the order statistics. Okay, xn is not there. Xn, f theta of xn is 1. So what's cooking here? We have the original data x1, x2, xn minus 1 from a certain distribution f theta, unknown parameters theta, and we look at the ordered values of these x's, and then we define this f theta x0, f theta x1, and so on, and then look at the d thetas, the spacings that you so get. Theta is, of course, unknown, but that's not the issue right now. So di theta is defined to be f theta xi minus f theta xi minus 1. So these are uniform, these are supposed to be uniform spacings if theta is the true value. That's the key point. So we want to estimate theta so that this f theta, di thetas behave like uniform spacings. What do I mean by that? So in other words, find theta that brings the observed spacings, these di thetas, as close to 1 over n as you can. So that is the method of estimating using the spacings. Theta could be a vector, as I said. So here is the deal. So F1 is the d1 theta, dn theta. F2 is a, say, 1 over n, 1 over n. So you have two distributions, maybe multinomial. And then look at these and you try to find a divergence measure between F1 and F2 and make it as close as small as possible. So here what kind of divergence measures? Here is a scissor divergence, which is for a convex function h. H between F1 and F2 is defined to be this measure there. And this is not quite a metric, but it has most of this divergence. It's like Kullback-Leibler distance, but it's Kullback-Leibler is a special case of this, of course. And so the problem now, estimation problem is, look at the h of theta. H is a function that you pick. And so this is the quantity I want to minimize. Find the minimizer of theta hat of this h theta. Okay? So that's the spacings estimation. What are these di thetas again? They came out of the f theta that's unknown, but nevertheless, theta is an unknown parameter, and h is a given function that you choose. We'll talk about what functions to choose later. Okay. So here is to convince you that this is an interesting enough idea. If you have observations from the uniform 0 theta, MLE is the sample maximum. Whereas if you do h of x to be log x, you get the spacing space estimate to be n over n minus 1 times its sample maximum, which is the UMVUE. Okay? So in other words, the UMVUE is spit out by this method spacings estimation. Similarly, if you have a rectangular distribution, uniform distribution, theta minus half to theta plus half, then you can show that with any of these h functions, that theta hat turns out to be x1 plus xn minus 1 over 2. Whereas MLE is any value in between those two numbers. MLE is not uniquely defined. Whereas this, you end up getting the spacings estimation gives you that nice estimator. And then there are some nice results that say that the spacings-based estimator, theta hat, has asymptotically normal distribution. And with a complex-looking variance value, and that variance is also based on this h function, and w is our exponential. So these are consistent, asymptotically normal estimates in the case of, what are we talking about here? This is, these are some results on the maximum spacing estimator. It's consistent. These are some of the results by different people that I'll skip at the moment. That if you have now estimation based on higher order spacings. Now, I talked about one-step spacings, gaps between one point to the next point. Now, I'm going to look at a same problem, f theta, theta unknown, let this be the density function, and then we want to estimate this theta using what I call higher order spacings. Let's see. Okay, so that's our divergence measure, and following the distance-based estimation. So this is the idea. We look at the density estimator f hat of some kind, and look at this f. Find a theta that makes this s h theta hat. This is the sample representative f hat x. Okay, I'll tell you more about it in a minute. So they find that theta which minimizes the divergence measure given by this. And for example, Beran in 1977 proposed this estimator. Hx is half of 1 minus root x square, and that's called the Hellinger distance. And This is the minimum Hellinger distance estimator. What is the minimum Hellinger distance estimator again? Is the one that minimizes that SH theta for this particular choice of H. But this is another paper that talks about how to get this minimum Hellinger distance estimator. And now we want to get into higher order spacings in the following sense. What are higher order spacings? We have the original framework that the f theta x1, f theta xn, the same setup that I had. But instead of taking successive observations, I take m steps at one time, where we'll assume without loss of generality, m is an integer and k is n over m. So you get k such spacings. What are we talking about? If you have, for example, 5 observations, then if I take, for example, m to be 2, I jump from 0 to 2, I get d1, 2, I get jump from 2 to 4, and 4 to 6. 6 is my 1. So I get 3 two-step spacings. So this idea, in fact, this is the higher order spacings m for any m. And there are results, there's a lot of different results that show the larger the m, the better the tests become. And the estimators also get better. So the question we were raising in this particular paper is to ask ourselves, the question of what if m is also let go to infinity, and we let m and n go to infinity simultaneously. So what are the optimal properties of estimators, and what kind of properties does the estimators have? And here is some assumptions that we have. These are pretty standard assumptions that one makes even in the MLE context. And so we know for a fixed m, asymptotically optimal generalized, GSE is my notation for generalized spacing estimators. What is generalized spacing estimator? Those are that use m-step spacings, for example. We know for any m, there are results that show hx is minus log x is the optimal quantity. But if m goes to infinity, then the asymptotically optimal estimator is no longer unique. It turns out, if you look at the so-called power divergence measure, this is a family of power divergences. Box-Cox transformation has something to do with this. In fact, this goes back to Rennie, 1961. He has a divergence measure that's connected to this. And Hellinger distance is a special case of this, and lambda is a minus half. So we look at this class of power divergence measures, power divergence statistics. In other words, this is a subclass of the so-called the other bigger class that I introduced earlier, convex functions and so on. This is a special case. And then we show that under general assumptions, if m goes to infinity and m over n goes to 0 as n tends to infinity, then the GSEs based on this subclass of H divergence, subclass is this particular minimum power divergence that we're talking about. They are shown to be consistent, asymptotically normal, and asymptotically efficient. Asymptotically normal, asymptotically consistent are known, but they are all asymptotically efficient. These are all long proofs and long results that are, I'm not going to get into those, but here is what, for example, here is the relative root mean square error for different GSEs. I picked, for example, in the power divergence statistics, lambda to be -1, lambda to be 0.9, lambda to be 0.5, and then we are looking at the relative root mean square error of estimators compared to the MLEs. How do these GSEs behave with respect to the MLEs? And it turns out the GSEs they behave just as well as the MLEs. In fact, see the y-axis up to 1.05. Some of these statistics are the blue dots, these blue, red, green, they're all the GSEs. And they end up with competing very well with MLEs. And in fact, they do better than the MLEs in asymptotically. So these are simulations, and these are also theoretical results that say you have a whole class of spacings-based estimators using that power divergence statistic that compare very well with the MLEs. And you might say, well, if they compare just as well as MLE does, why use only MLE? Then we say, okay, then the question is, what is a good choice of M? And then there's a bootstrap idea that I propose here, that you can pick M to be, you can pick M in this usual, kind of data-based approach to finding a M, optimal M, as the one that minimizes that quadratic. Okay. Now, what is more important, what I think is more impressive, is that these estimators that we have are robust under contamination. And that is not a property enjoyed by the normal distribution for the MLEs. For example, we have a G, which is the parameter theta naught, normal mixture. Phi is the usual normal CDF, and the H is a, contaminating distribution. And so there are observations that come from. So we think we have data from phi of x minus theta, but there's a epsilon contamination. So there is a maybe 10%, 20% contamination coming from the distribution H. And the question is, if you have a distribution G from which the data is drawn, is the phi, which you assume it is the normal distribution that you are estimating the mean for, then how do these estimators behave? How does the MLE behave for the theta naught? And it turns out, here is a graph, I don't know if you can see it well enough, but it turns out this is the x-axis is the one that shows the contamination, 30% contamination, 40% contamination. Even then, the MSCs, the GSCs that I talked about, they have no error in terms of, they come out, the root mean square error is very small. Whereas the root mean square error for the MLE blows up all the way there, almost 4 times as much. So what is the model of this? If you have potentially contaminated data, then the GSCs are a better bet. They do much better than the what the MLE would do. So this is the finer point of these GSCs, and these are all simulations. But I think I'm almost done. I'll summarize what I was saying. A family of methods based on higher order sample spacings, size going to infinity, with M step size going to infinity with sample size. And these are called generalized spacing estimators. And these have been shown to be consistent, asymptotically normal. And GSCs have power divergences. If the particular power divergence based GSCs have asymptotically efficient when the order of spacings goes to infinity. This is a, and then unlike the MLAs, some of these estimators have been shown to be very robust under heavy contamination, as much as 40% data contamination. And bootstrap may be used for adaptively selecting the step size. How large steps should you take? The M, that bootstrap may be used. Here are some references, and I'll in particular point out Caesar, and I think I'll point out to the particular paper that we are looking at, this Ekstrom. So the paper on the top of this page is the one that's coming out in test. That is the paper that I summarized in the second half of my talk. And there are questions about higher order efficiencies. For example, second order efficiencies of spacings, those kind of things, Edgeworth expansions, those kind of things are discussed in this paper. And Pike is the basic paper I referred to. And this paper here, the second paper here, is the one where we talk about multidimensional. What does one do in multidimensions? What does spacings mean in 2 dimensions or more? You can use Dirichlet tessellations or nearest neighbor balls and things like that. So there's that paper, and these are some of the references. Well, I think I'm done. You want this?
You mentioned robustness
Yes.
of these estimators. Is it possible to derive some influence functions or the breakdown points?
Yeah, no, we haven't explored those yet. We simply did the so-called epsilon contamination and seeing how the estimators behave under contamination. But yeah, that's a good point. One should perhaps consider that idea.
Any other point, please? Okay, so thanks all speakers again. And this concludes our